Hello, everyone, and welcome to this last session of our deep learning series. Today, we'll be covering data parallelism using PyTorch DDP. This is an update of our video and also multi-GPU training using Horovod. So we'll be covering very similar topics, but using PyTorch DDP approach instead of Horovod. My name is Ignacio Salasua, and I'm a solution architect leading the NVIDIA AI Technology Center in Iberia. And today I will be your instructor for data parallelism using PyTorch DDP. So let's look first at our agenda. We will start by understanding why do we need multiple GPUs and the benefits that this brings to our deep learning pipelines. Then we'll move into understanding a bit better what data parallelism means and how PyTorch approaches it. And finally, we'll see the integration of PyTorch DDP into our toolkit with two examples, one using torchvision and another one using DALI. So why do we need to use multiple GPUs and what are the benefits of this? And it's something that you already saw in our lecture using Horovod, but nevertheless, it's always good to refresh it. So one thing we've been observing throughout the years is models or deep learning models have been becoming larger and larger. Thanks to this, we are able to solve more complex tasks. However, this of course comes with more computing power that we need. Actually, to give you a reference on the computing power, if we would try to train one of these models on a typical dual CPU server, it would take us around 100 years to be able to reach convergence. Whereas if we train it in our latest DGX H100, which is powered by 8 100 GPUs, it would take us around a month to reach convergence. But not only we need more compute, we also need more data, right? These trainings need larger and larger amount of data as the model gets larger. Of course, in the beginning of feeding data into our model, we will be in a region where it's what we call kind of best guess ever, since it's not going to be enough for the model to build proper boundaries for deciding classes or whatever task we're looking into. But then we will actually reach this region where we do see a negative correlation if we look into the error, or positive correlation if we look into the performance, or let's say accuracy, between the amount of data we feed into the model and the basically performance of the model, right? But as everything in life, this has its limits. And of course, at some point, we will not see much of a benefit. An intuition behind this is if we look into, let's say, MNIST, while in the beginning we'll see that the more pictures of numbers that we feed into the model, the better it gets. At some point, it has seen almost every way of representing the model, representing the number. So that's why it would not get better. Luckily for us, while we did see this correlation between the amount of data and the model complexity, this relationship is sublinear. So this is actually very good news for us, because that means that while our models are becoming larger and larger, our datasets will too, but not at the same pace as our models. So we don't have to, because otherwise it would be infeasible to have such large volumes of data. But one of the implications of having these more complex models and also larger amounts of data is the training time that it takes. So for example, if you would look into how long it would take to train a Res 950 back in 2015, this would take around 30 hours. Whereas now, or like in latest years, thanks to the usage of multiple GPUs at the same time, we're able to reach around, train the model in around 8 minutes, a bit more than a minute. This not only has implications in terms of saving us time for other tasks, but also it has a direct implication in our performance. Since the lower the training time is, the more we can iterate and modify our model, and therefore reach better accuracy. And actually, we can see an example here in the beginning of ImageNet Challenge. Um, all the teams had around 25% of the classes wrong, whereas in latest years, at least in 2017, more than half of the teams had only 5% of the classes wrong. And probably with the statistics nowadays, it's even lower since people are using more and more GPUs and they can actually adapt better to the challenge. So to summarize this part, one thing we're observing is model complexity is going up, and therefore so is the dataset size, and therefore is also the training time, right? So there's three things that are going up, and it's not desirable since this takes us longer to train and so on. The only thing we can control out of the three of these is the training time. How we can do that? Basically by leveraging multiple GPUs, right? So if we parallelize our training into the different GPUs, this reduces significantly the training time. Now the question is, how can we do this? One possible way of parallelizing our training into several GPUs is using data parallelism. There are other ways of parallelism, such as model parallelism, but in this workshop, we will only covering data parallelism. So to understand data parallelism, let's refresh how the training on a single GPU worked, and then from there on, we will continue. So on a single GPU, we will have first, we'll be reading some data, right? We'll move this data into either CPU or GPU, depending where you're planning to pre-process it. Then you will pre-process data, queue it to create some batches that will be fed into the model. Then we'll transport the data into the model. And from here, we will be first calculating the activations for layer 1, then layer 2, and then finally the output. This output will be used for computing some loss, and then we will backpropagate the loss through the third layer first, then the second one, and the first. We will use this to execute the optimization step and update the weights, and then we'll just iterate. So in a multiple GPU setting with data parallelism, the first change comes here. So instead of reading the data only once, what we do is we'll split the data in two chunks, so two subsets of the data. So if, let's say in a system where we have two GPUs, each GPU will have half of the data. And then we transport this data into its corresponding, again, CPU or GPU, depending where we do the training, pre-process it, queue it to create batches, move into the model, and then here we'll have a model which is basically a copy of the same model, right? So it will be initialized exactly with the same weights, and it will be a copy of each across all the GPUs. So then here we compute activations for the first layer, second layer, and third layer, compute the loss, and then here backpropagate to the third layer, and here's the first second difference in a multi-GPU training. So here, what we do is we will average these gradients across all the GPUs, do the same for the second layer, and finally for the first layer. And then we'll be using this average of all the gradients to compute our decision step and to update our weights. And then finally, we'll just iterate over and over as we just saw before. Okay, so here then we have different things that need to be taken care of, right? First, we need to be able to split the data, and this is something that might not be as easy since we don't want to have all the time the same data into the same GPU, since we've seen in other lectures that this randomness behavior is actually desired. Another thing we need to do is we need to copy and initialize the model, as I was mentioning. And this is also something that it wouldn't be so easy to do manually, but we have to have some tool that allows us to copy the model, initialize it with the same weights, and create this communication. And then finally, we need to also make sure that this coordination of the gradient averaging is properly done, and that we wait until all the GPUs have compute the forward pass and so on. And also that the AI parameters are updated properly and with the right gradients. So for all these operations, as I was saying, there are different frameworks. In another lecture, we explore Horovod, but in today's lecture, we're going to explore the PyTorch approach to doing data parallelism or distributed data parallelism. The reason why we are focusing on PyTorch for this lecture is because we've seen that the community has been using more and more PyTorch throughout the years. So I think right now it's around 80 or 90% of the papers out there are written in PyTorch. So we thought that it would be interesting to explore their library for DDP. Okay, so before I start explaining how DDP works on PyTorch, let me give some small vocabulary or some terms that we need to know before. So first of all, the concept of worker. So for those that are familiar with other parallelism structures or parallel computing, a work is the same as calling a process. So basically, in our case, so in these deep learning models, a process will be, so each process will be taking care of training the model in a single GPU, right? So basically doing all this forward pass and backward pass and so on, also the processing of the data, the queuing and so on. This will be a process that will be taken care of. So basically, we will have as many processes as GPUs we're using, and hopefully as many GPUs you have available in our cluster. And the total stored number of workers will be our world size. Other concepts that we need to see, these are more related to the cluster and the relationship between the cluster and the processes. First is, let's say we have this cluster. The cluster has two nodes in it. So with basically two separate nodes with the different GPUs and they're connected between them. So in here, each node has two GPUs. So in total, the total number of GPUs we have available is 4 GPUs. Then what we'll do is for each process we'll initialize. So in this case, let's say we have 4 GPUs, we can initialize up to 4 processes. So have a world size of 4. Each of these processes will have a unique identifier called rank or global rank. This is going to be useful because sometimes we want to know which process is coming, particularly if there are certain operations that we only want to do once for all the training. Let's say, and we will see this later more in detail, but if you want to output some progress of the training, you don't want to be doing this for each process, but you only need to do it once. So in this case, you can just take one of the process with a rank, let's say rank 0, and say, okay, only rank 0 is allowed to output these operations, but the rest of the process can ignore this. This way, you don't have 4 times the same printing in your training. Another concept is also the concept of local rank. And as you might see here, local rank is a unique identifier, but only per host or per node. So as you see, we have a local rank 0 and 1 for the first host. And then we have a local rank 0 and 1 also for the second host. Why do we need these identifiers? This will have different benefits. One, as you see, we will be pinning the process of the local rank 0 to the GPU 0. So that's would be a one way of seeing it, as in, because you know, basically it's a way of choosing which GPU are we going to be using. But also, let's say if you want to do some also operations as in downloading some data set that you want to do once per node because you don't want to be reading the data set across nodes. This is something that you might want to do only once per process in each node. So here, only local rank, for example, 0, will be downloading the data. And we'll see that more in detail little later in a small snippet of the code. Okay, so now that we understand how data parallelism or distributed data parallelism works, let's see how we can integrate the PyTorch language into our own code. For that, we will be using our own NVAITC Toolkit, which I encourage you all to check it out. Here you have a lot of examples on how to integrate the different parts of the tools that we've been seeing throughout this lecture series. So, for example, mixed precision, DALI, and so on, into a single code repository. In particular, we'll be looking into 2 different parts. We'll be looking into how to train this on a more regular PyTorch workflow using torchvision, and also in a workflow using DALI, which is our own solution for data augmentation. So first, let's see how we define each of these workers that we were talking, so each of these processes, and some of the variables that we're going to be needing for this. So let's say you have your main function, right, that you will launch once you run your script. These will be basically changed to, and there's different ways of doing this, but for this example, we'll be using multiprocessing spawn. So what we do is we say, okay, in our main function, please launch as many workers as GPUs will have available. So you say here, spawn takes worker, which is basically a function that we'll see now that will be defining the different variables, and we'll be calling the training functions. Then says how many processes we want to launch. In this case, as I was mentioning, we'll be doing as many GPUs as we have available and per node, and then finally also the arguments that we will need for our training that basically come from the parser. So let's look into the worker. So the worker, as I was saying, is basically a function that first we'll be using for taking or defining different variables. So we can define the global rank as the node ID. We'll look into what the node ID is exactly, but it's basically the identifier of the node you are right now running the code from. Then the number of GPUs per node plus the local rank, which is already coming from basically spawn. And then we initialize the process. Sorry, is the computation. Then here we will initialize the process. In this case, we just need to tell, okay, for each process, you call this function, then you tell which is the backend that you're gonna use for the process to communicate to the other processes. In this case, we choose Nickel, which is an NVIDIA library. There are other options available also. Then, okay, how many processes are in total in this training? And then what's your unique identifier or global rank? Then we'll also define the device. And as I was mentioning earlier, we can use the local rank for this. So we'll say, okay, whatever parts of or this training is going to be basically linked to this particular device. So we're going to, if we have to move things to GPU, we're going to move it to this particular device. So in this, let's say if it was processed with local rank 0, it will be moved to the GPU 0. Again, there will be 2 GPU zeros, one per node, of course. And then also sometimes you want to say, okay, if we have several, so if you are have several GPUs available and we're using distributed, this might change some parts of the training, so that we have this distributed variable that we're going to use later for some conditional statements. Okay, so now that we've seen how to initialize the process, we also need to prepare the model, as I was saying, and it's quite simple. So first, we need to move our network into the device that process is linked to, as we saw in the previous slide. And then once it's moved, we can just wrap it with this function from the torchvision parallel library. It's called distributed data parallel. And then if you run the network, basically it will already take care of initializing the process, initializing the network with all the same weights and copying it across all the GPUs. So as you see here, all it takes is basically the actual network and then the local rank of that network. And then it will already take care of initializing it through all the different GPUs. Another thing that we need to do, as we was mentioning when we talked about the data parallelism in general, is we need to do the partitioning of the data. And as I was mentioning also, it's important that we cannot feed the same data to the same GPU. Same way that you change the order of the batches, you also want to change the data you feed to each GPU to increase the randomness of the training. So first we need to shuffle the data, and then we need to split this data across all the workers. And this is something that is also easy to do with PyTorch DDP. So here we will see the first difference between our torchvision code and our DALI code. So for the torchvision, it's quite simple. We just use also from from PyTorch libraries, we can use the distributed sampler, and then this will already take care of splitting the data in chunks and also taking care of the shuffling. And then good thing is we can, once we define the sampler, we can just feed this into our typical torchvision data loader, and in there it already takes the variable sampler, so you just feed it into it. Now, when it comes to DALI, this is a bit different. We won't be using the distributed sampler, but already DALI has kind of integrated this sort of behavior in its pipelines. So basically, if you use the proper shard ID and the number of shards, it will already take care of splitting data across the basically all the shards. Also, in this case, all the GPUs. Not only we need to, as I said, sample the data, we also need to make sure that we update the sampler every epoch. So basically, every epoch, we're going to be shuffling data, as I was saying, right? So in every epoch, each GPU will be receiving a different subset of the data. And also, it's important that once we have the subset of the data, we feed it into the proper device. And again, this was defined earlier using the local rank. In DALI, again, we don't need to take care of moving the data into our GPU. This will already be integrated in the actual pipe. So just make sure that you define properly the shard ID and the number of shards. And one thing that I don't have here on the snippet of the code, but it's also relevant, is something that I was mentioning earlier when I was talking about local rank and global rank. And I promised you to show you a bit of how this looks into the code. So here it's a perfect example of how local rank and global rank might be relevant. So let's say we first want to download some data set, and we want to be doing this once per node, right? As I was mentioning earlier. So in this case, what we'll be doing is, okay, only the process that has local rank 0, this is what's going to happen once per node, downloads the data. And also very important, until this hasn't happened, the rest of the process cannot continue on the script, because otherwise we may reach a point where let's say process with local rank 1 tries to do something with the data, but the data is not there yet because local rank 0 hasn't downloaded yet. That's why we're going to use a barrier to make sure that all the processes stop there, and only once the local rank 0 has reached out that point, they can continue. And another example of here of rank, and in the case global rank, as I was mentioning, is when you're trying to print some evolution of your training. This is probably something you want to only do once, regardless how many processes you have, since at the end we are averaging the gradients and so on. So that's why we're going to take the process with global rank 0, which only happens once for all the GPUs across all the nodes, and let it take care of the printing this evolution of the training. And then finally, for our script to be able to run, we need to define some variables. So we first can define the number of nodes that we're going to be using, the node ID from where you are launching the experiment, and also the number of nodes, the GPU, sorry, that you're going to be using per node. We can calculate the total world size, so the total number of workers / processors we'll have. This can be calculated by multiplying the number of GPUs per the number of nodes. And that's it. We also define some environment variables, and then finally, if we want to just basically run it, and again, this works because we're using, as I was mentioned earlier, the multiprocessing spawn. You can basically just now use the typical Python running script command. So basically, you will just do Python, the script we're going to be running, and then the number of nodes and the number of GPUs, of course, because these are two new variables that we need. And that's it. And then your already variables you had already defined as batch size or the data. So that was it from this. Just let me recap a bit of what we've seen. So one thing we need to do once we launch the process is to make sure that we initialize each process properly using init process group. Then we need to also make sure that each worker or process has its own GPU assigned, and we can use the local rank for this. Then we need to wrap our model using the DDP function to make sure that all the copies of the model are initialized the same way and they're also updated the same way. We can use the distributed sampler to shuffle and split the data across all the GPUs. And finally, barriers are going to be very useful for us whenever we want all the processes to be synced and stop at some point until, and make sure that they do not continue until all the processes reach a certain point in the code. This was, for example, relevant when downloading data. So before I wrap up, some tips that might be relevant for you now that you are be using larger batch sizes. So one is you need to multiply your your learning rate by the number of GPUs that you're using. This is something that you see here in the first paper I linked here, where they have the explanation for this. So yeah, I encourage you to check it out. But as a quick note, it's basically just multiply your number of your learning rate by the number of GPUs. Then one thing that you might be able to use is batchroom sync, which is basically synchronize the batchroom statistics across all the GPUs. I would only encourage you to use this if you have small batch sizes per GPU. Otherwise, this will slow down the training process, basically because you have another layer of communication. So if you already can fit a decent amount of samples or batch size in each GPU, this might not be needed. And finally, because you're also now using larger batch sizes, you might run into some issues. So maybe you also want to check out some other optimizers such as Lars, Novograd, that they work much better on larger batch sizes. And that was it from my side. Before leaving, please make sure also you check our developer program. In there, you'll find a lot of SDKs, a lot of software has been optimized for GPUs, also a lot of training resources like the one you just saw. Also, there's a big community in there, so you have a lot of people that participate in forums. They also organize meetups and hackathons, and it's actually something that's for free. So yeah, you should definitely check it out. And that was it from my side. Thank you all for listening. And as I was saying before, check out our toolkit where you can find all the snippets of the code.